In this video, we have a discussion on alpha-beta pruning, a technique designed to make the Minimax algorithm more efficient. The main issue with Minimax search is that the number of game states it must explore is exponential in the depth of the tree. So the time complexity was order of b to the power m. This makes Minimax impractical for many real games such as chess, where the branching factor is 35 and total number of moves is around 100. So this becomes a very, very, very large number. And although the exponent cannot be eliminated, we will try to see if it can be effectively cut in half through pruning. The idea is that correct Minimax decision can often be computed without examining every single node in the tree. The technique used for this is called alpha-beta pruning. When applied to a Minimax tree, alpha-beta pruning returns the same decision as Minimax would. The only difference is that it prunes away branches that cannot possibly affect the final decision. Please remember, the final decision will still remain as it could have been in Minimax, but probably checking only half of the branches. Let's see this more practical example where A is the max and the next layer is the mean, and in the mean there is one branch which is B and the other branch C where the queen is being attacked by mean. And from C we have a option to go to which is checkmate of A or the max. So no matter what is the evaluation of the other children of C, you don't really want to go to C because you might need to go to checkmate then. Whatever be the other option, it doesn't really matter because mean will then take you to checkmate. For mean, because remember, max will play the first, then mean will play. At this level, when mean has a choice of attacking your queen and checkmating you, then definitely mean will take you to this direction instead of this, even if it is better than this. This is to understand. Let's see the next slide. So because mean checkmates you, so in E there is -1, and let's see there is a draw option which is half, you get -0.5. So max in A avoids C because B is better, you have some positive outcome. At most max gets from C is a -0.5 because this is a max node. So max will say, okay, from this I do not want to be checkmated, I'll somehow stop opponent and draw the game, and you get -0.5. The maximum among these two is -0.5, so that's the best you can get. But if you go here in B, you get 0.3. So the subtree in G can be just cut as soon as I receive the value of D. Once you know the value at D, maximum is -0.5. And by that time, because it's a DFS, you have already explored this side, you know the maximum value I can get from here is 0.3, and from C I'm kind of getting -0.5. So A will say I'll not even go that direction, I do not even need to consider value of G, I'll stick with this as my optimal path. Since A is independent of G, the tree under G can be cut. So now let's see how the Minimax algorithm works. So there is a pseudocode which basically, the alpha-beta search algorithm, it returns an action. So you see what is the maximum value a max can get. It can be some big positive number. So if it fails to get that, it sets its value to something which is -infinity. That means, oh, I failed to get the positive value. And max thinks I want to minimize the mean thinks I want to minimize max's value to as negative as I can. But if I fail, that means max will be happy to increase its value to positive infinity. So mean will see that, okay, positive infinity is max's value, I need to drag him down from there. And max thinks my value is -infinity, I need to increase it from there. So we initialize them with these values. And then we try to repeatedly check it. So we check the terminal, go to the terminal of the leaf node and see the utility and set the value. So whenever it's a max node, I set the value to minus infinity, and when the value is a min node, I set the value to plus infinity. So this is the overall pseudocode. See, it's for max, the value is minus infinity. For min, the value is plus infinity. And then you keep updating them. So let's see how it works. So that's exactly explained here. For its alpha with respect to beta, the best value, and with respect to for beta is with respect to mean. Okay, so now let's see this example here, which is basically to understand the idea of alpha beta pruning. We consider this 2-ply game tree, okay, similar to the one used earlier for Minimax. If the Minimax algorithm applied here, every leaf node would be evaluated. However, with alpha beta pruning, some leaf nodes can be skipped. Let's see how. For example, in the calculation shown in here, the successors of node C, which is this one, A, B, C, and D, this is C, okay? So successors of node C have values that are not evaluated. We have written them cross, means they have not been evaluated. Suppose they were labeled as X and Y. Even without knowing their values, it becomes clear that the final minimax decision at the root does not depend on them. So let's see how it works. So it's a DFS. So we come down here and we check. Oh, this is 3. So mean will choose something. Let's say 3. And then it will evaluate other nodes and see, oh, this is 12. So definitely greater than 3. So mean will not choose that. And then it will also evaluate 8 and then say, oh, this is also greater than 3. So 3 will be the minimum value for this node. Now 3 is taken to its parent, transported above. And then this branch is being evaluated. And I see there is a 2. Oh, 2 is good. Mean is thinking because this is mean now. So it says that I need something less than equal to 2. Any other nodes, whatever their value are, even they are 1 billion and 2 billion, will mean ever choose them? No, it will not choose them. So in that case, max will never care for exploring what are in those branches. Do you understand? So this is from max's perspective. Max will never explore. It has already seen that, oh, this path gives me 2. Whatever the other nodes are, mean will not give me even they are bigger than 2. So I do not care about what they are. Trim those branches. So then you take that 2 above, and then you see we already have a 3 max. Now this is max's turn. Max will say, oh, I already have a 3. I will never choose a path with a 2. So now let's explore this third one. And then it will explore, oh, this is a 14. Max, this is min's path, but max will say, oh, I'm increasing my value. So let's see if I can get something 14, but this is a mean node. Mean will choose, always look for something less than 14. So mean will explore the next one and see, oh, I got a 5. So he'll change 14 to 5. And then you check the third branch and change 5 to 2. So then finally max will see the best or optimal route is this one. You see, if mean does not play optimally, max will be able to choose 14. But since mean also plays optimally, max gets 3, which is better than 2 or anything less than that, and it will take that 3. So this is to understand. This is very important. And so regardless of the value of x, this 2 branches, I could still take the optimal path. Okay, so now so the general principle of alpha beta pruning is very straightforward. Suppose there is a node n somewhere in the game tree. If a better option has already been found, either at the parent of n or farther up the tree, then node n will never be chosen in actual play. Okay, so like let's say here, if a better option is already found above, so I found a 3 here. When I come to check 2, I know there is a 3. So then I will say, oh, I get 2 or less, so I do not need to explore them. So that's as simple as that. Once this conclusion can be made, then node n and its descendant, so this nodes can be pruned. That because I have some value higher in my parent, I'll definitely not go for anything less than 2. Because minimax search is depth first. At any one time, only the nodes along a single path need to be considered, okay? But we take them to the parent and then explore others. So when we come here, we actually know what's the value in the parent.